All right, team, we got a short section today, which is really piggybacks on the theory that we developed in 8.1, looking at the probability distribution for the sample mean. So we can play the same game with other statistics, right? So whatever parameter of a population we may be interested in, we could also ask about the distribution of its corresponding statistic among a selection of samples, all of a fixed size. So in this section, we're going to look at the distribution of the sample proportion. So the idea here is that we have a population and we're interested in a particular quality among the individuals in that population. So this quality is either possessed or not possessed. So it's a yes or a no. It's actually binomial. So for instance, we could ask people in the population, do you think that you need less sleep than other people? The answer would be yes or no. And if we're interested in the proportion of people that say yes, then we would call that P. And P would be the parameter, the proportion parameter for the population, which would be the number of people that said yes to our survey over the total number of people in the population. So this is a parameter of a population, something that either we can't get our hands on or we can. In some cases, this is something that can be given to us. And now, instead of using samples to understand populations, often we can use populations to help us understand samples, because the truth is, when we're working as surveyors, we're working with samples. And one way we can look at it is samples approximate populations. But the other way we can look at it is that the population gives us an ideal model for the different kinds of samples that we could possibly get. So let's stick with the idea of the survey where we ask people whether they've gotten enough sleep or not. We can say that we had some big census, Gallup poll or something, and we got an actual figure for this number P. Well, we know that when we take a random sample out of the population, that that particular handful of people won't necessarily reflect the proportion of people in the population that answered yes to the survey. And so when we calculate when we ask that particular sample of people whether they need more sleep or not, X1, many of them say yes. And so we get a new proportion that's approximate. This is an approximation of this population proportion. So this is the proportion of people within the first sample that said yes to our survey. We could take another sample and go through the same song and dance, compute another proportion. This is now a second approximation to the P for the population. We can take as many samples as you like, K many samples, and we can have the Kth sample proportion for this particular quality that we're interested in. So whether or not people need more sleep or not. So just as we did with the sample mean, we could ask, how do we think these sample proportions are distributed with respect to the global mean of the population, or not the mean, but the global proportion of the population. So we suspect that they are somehow distributed about this P, because they're all approximations of that P. So they're probably dancing around that P. But how are they distributed? And what is the mean of that distribution? And what is the standard deviation of that distribution? That's what this section is all about. Okay, so let's define it officially. The sample proportion, which we call P hat, which has that little hat on the top of it, is given by P hat equals X over N, where X is the number of individuals and with a certain quality within that sample, and N is the sample size. Okay, so as we move forward, you might notice that some of the mathematics that we see here looks a lot like the mathematics that came out of the binomial probability distribution. And there's good reason for that. Because this proportion is generated by asking basically a yes or no question, either you have the quality or you don't have the quality, the behavior, the mathematical behavior of this p hat, this estimator of the global proportion, behaves a lot like a binomial random variable. So it basically is binomial random variable, but we still want to treat it separately because we want to think of it conceptually as something different. Okay. So, quick example. Say we take a survey of 1,200 people, we poll 1,200 people and we ask them, do you work while you're on vacation? 552 said yes. Find the sample proportion. So sample proportion is the number of people that said yes over the total number of people that were surveyed. So that's 552 divided by 1,200. And that gives us 0.46. So it's really that simple. That's what the sample proportion is. Again, the thought here to have is that p hat is 0.46. This 0.46 applies to a sample of a greater population. So if we were able to ask everyone in the world this question and then compute this proportion, we'd get a value for p without the hat. And that p will differ from this 0.46. But this 0.46 should be relatively close to that p, unless this was an unusual sample. Okay, so just like with the sample mean, now we're looking at the sample proportion and we're interested in its distribution, which means we're namely interested in these three qualities: shape, center, and spread. What is the shape, center, and spread for this estimator p hat? So we saw with the sample mean that the shape was approximately normal, that the center was equal to the global mean. So the population, the mean of the distribution of the sample mean was equal to the population mean, which sort of makes sense. And then we saw that the standard deviation was related to the standard deviation of the population, but it was divided by a square root of n. So it was scaled according to the sample size. So that's the way that the shape, center, and spread worked for X bar. Now we're looking at p hat. What is the shape, center, and spread? Okay, so shape for the distribution of our p hat estimator is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. Okay, so this looks a little weird, but if we remember, or if you recall that I said that p hat is essentially a binomial random variable, then this expression is basically equivalent to saying that we want the variance, or I should say the sample variance of this proportion for this sample to be greater than or equal to 10. So that's makes more sense. We put this limit on the variance, which in turn puts a limit on the standard deviation. And as long as the variance is large enough, then we say that the shape of our distribution is approximately normal. Okay. The center, which is to say the mean for p hat is mu sub p hat, which is equal to the numerical p. So the p for the population, which is the global proportion of individuals with this certain quality. So notice this is just like with the sample mean. Our our mu for the sample mean distribution was equal to the actual global mean, the population mean. So here the mu for the proportion distribution is equal to the global proportion. And then finally, what about the spread? The standard deviation for our p hat is equal to, oops, coming back, there we go. The standard deviation for p hat is equal to the square root of p times 1 minus p over n. So again, this looks a lot like the standard deviation for a binomial random variable, but it's being scaled according to this n. So just like we saw with the sample mean standard deviation. Okay, so that's the shape, center, and spread for the distribution of the p hat estimator, the sample proportion. So let's look at an example. All right, so we're told that the proportion of Americans who believe that morality is in decline is 0.76, and this was generated by a Gallup poll. So this 0.76 that they're telling us in this problem is equivalent to the global proportion of people that believe morality is in decline in America. From that population, we take a random sample of 60 people, and we are interested in what is the shape of the distribution for this particular estimator. Okay, so here we're not looking at one specific sample. We're just interested in what is the likelihood, what's the likely characteristics of the sample that we take. So we haven't haven't actually processed the data for our sample yet in this problem, where we've taken the sample, we've got all 60 people in a room, and before we even ask them a question, we're interested in what's the likelihood of getting certain results. Okay, so we're going to describe the distribution of p hat here. So you want to think shape, center, spread. So shape, first thing we want to look at is n p times 1 minus p greater than or equal to 10? That's the question. So n here is 60, p is 0.76, 1 minus p is 0.24. So we're going to multiply these three numbers together and see what happens. So that's 60 times 0.76 times 0.24, and we get 10.944. Okay, so 10.944 is definitely greater than or equal to 10. So that implies that p hat is approximately normal. And remember, we would say normal with a mean equal to p and a standard deviation equal to the square root of p times 1 minus p over n. And whenever we use this particular notation, we actually always write variance. So I square it, but I like to keep it in the standard deviation form so we know what the standard deviation is. Okay, so we're describing the distribution here. We've determined that the shape of that distribution is approximately normal. We find the center. Well, we know that the center of our distribution is equal to 0.76 because it's equal to the global proportion. And then we look at the spread. And here we're interested in the standard deviation for the estimator p hat. And that's the square root of 0.76 times 0.24, all divided by 60. So We compute that standard deviation. Square root 0.76 divided by 0.24 divided by 60. Oops. And we get a standard deviation approximately equal to 0.22230. Okay. So this describes in full all the important aspects of the distribution: its shape, its center, and its deviation, standard deviation. Okay. So finally, let's look at how we can use what we know about the distribution of this sample proportion to compute probabilities. So as researchers, we often don't have the resources to conduct all these surveys. They cost money and they take time. And so what's better is once we know what the shape of the distribution is, then we can make predictions about what our samples will likely look like before we ever take the samples. And we make those predictions using probabilities. So let's look at this example. We're told that 15% of Americans have hearing trouble. Okay, 15% of Americans have hearing trouble. I immediately think 15% of Americans. Americans is a population. So this is a population proportion. We're asked, if we take a sample of 120, we want to find the probability that at most 12% have hearing trouble. Okay, so what we want to think about here is, out of all possible samples of size 120 that we can take from the population of Americans, there's a certain amount of those samples which will have a proportion of people reporting hearing loss being less than or equal to 12%. Some will have more, up to, in excess of 15%, but we're only interested in those that report 12% or less. Okay, so let's see what the likelihood is that if we take a random sample out of this population, that sample will only have 12% of the people in that sample having hearing trouble. Okay, so the first thing we need to do in order to calculate a probability is we need to know what the distribution is for the problem. Now, the only distribution we've talked about in this context is the normal distribution, but we can't just assume that we have normality. We have to determine whether it's a correct assumption or not. So the first thing we do is check the shape, which means check n times p times 1 minus p. What does that equal? Well, our n is 120, our p is 0.15, and our 1 minus p is 0.85. So we're going to multiply those three numbers together. Scooch this up. So 120 times 0.15 times 0.85 is 15.3. So 15.3 is definitely greater than 10. So just from this computation, we can conclude that p hat will be distributed normally with a mean of p, and which I should just write it down, with a mean of 0.15 and a variance of 0.15 times 0.85 divided by 120, all square rooted. So that's n squared, that's the variance. Okay, so now we know what the distribution of this parameter is. Once we know the distribution, now we can compute probabilities. Okay, so let me flip this over. So now that we know the distribution, we want to compute a probability. We're interested in the probability that at most 12% report hearing trouble. Okay. So if we translate that into mathematics, we say that's the probability that p hat is less than or equal to 0.12. Okay. Now we know that the estimator p hat is normally distributed in this case because we checked that to begin with. So in order to compute this, we can use the normal distribution. In particular, we can use normal CDF function. Okay. So remember, with the normal CDF, you have 4 inputs: the lower bound, the upper bound, the mean, and the standard deviation. So these are the 4 things that we need to tell it. So lower bound, this is a less than or equal to probability. So the lower bound is negative infinity. So we just use negative E10. That should suffice. And we're going to go up to 0.12. That's the upper bound. The mean we know is P, which was 0.15. And the standard deviation, which we ought to compute, but I'll just write down here, is the square root of 0.15 times 0.85 divided by 120. So those are all the inputs that we need to put into the calculator. So we can type it just like that. So remember, we do second vars, normal CDF, which is number 2, and then we have to put in the 4 inputs. So lower bound, we do negative second comma, gives us the E times 10. You really could just put negative 1,000, whatever you prefer. That's just how I like to do it. So up to the upper bound, which is 0.12, with a mean of 0.15 and a standard deviation of the square root of 0.15 times 0.85 divided by 120. Okay. Enter. And we get a result of 0.178692832. Okay. Nope. All right. So that's the numerical part. You can get the answer easily enough, and we can round this to 0.18. Okay. So getting the number is fine, but understanding a number takes a little bit of care, because we've got a lot of fractions and decimals here, and it can be a little confusing about what this number means. So let's rephrase the question and think about the result. So the question was, basically, if I take a random sample from a population whose mean is 15%, basically, whose global proportion is 15%, then what's the likelihood that that random sample that I take from that population will have a sample proportion that's no greater than 12%, right? So there are some samples that will have a sample proportion greater than 12%, but we're only interested in what fraction of all possible samples have a proportion that's less than or equal to 12%? And the answer is that out of all possible samples, only 18% of those samples have a sample proportion of 12%. I know, it sounds confusing. So, again, the thing to think here is, think of the picture. The sample proportion is normally distributed. Its center is P, which is 0.15. And we're interested in the amount, the fraction of the total area that is less than or equal to 12%. So it turns out that if we find that area, which is just that tail, that this tail is about 18% of the total area. So that's another way of thinking of it. This distribution represents all possible samples that you can take from the population, or it represents the sample proportions for all possible samples. So most samples will have sample proportions that fall within this area, the big hump. But there are some sample proportions that fall outside of that hump. And it turns out that this, all the samples that have a sample proportion less than or equal to 0.12 or less than or equal to 12% is as little as 18%. So that's the way to think of it. 18%, or 18 out of 100 samples, will have a sample proportion less than or equal to 12%. Okay. So let's look at a follow-up question to this problem. So we're still taking a random sample of 120, but now we're looking at a specific sample. We take a sample and we find that 26 out of the 120 claim to have hearing trouble. What we're interested in is this particular sample that we've taken an unusual sample, or is this a usual standard sample? Is it, in other words, when we're taking the sample, was the sample drawn from the hump, or is it drawn from a tail? Okay, so in order to assess that, we need to see what the likelihood is of getting a sample with this many people in it who claim hearing trouble. So first thing we want to do is find out p hat. So p hat for this case is 26 out of 120. So what sample proportion is that? We know that the global proportion is 0.15. The sample proportion for this particular sample is 0.21, and I'll say 217. Okay. So this particular sample has a lot more, or seemingly a lot more, individuals reporting hearing trouble than the global population proportion. So that tips us off that something might be unusual here, but unusuality, if that's a word, unusualness depends on the spread of distribution, not the mean. So just because this seems like it's far away, we don't know if it's far away until we compare it to the standard deviation. Okay. So now, in order to determine whether this is unusual or not, we need to see if we can compute a probability, because being unusual means we must be able to say that the probability of getting a sample with this particular proportion in order to determine whether this is unusual, we need to look at a probability of getting a sample with this particular proportion. Great. So in order to compute a probability, again, we need to know whether we have a known distribution or not for this particular case. So we start with asking about shape. What's the shape of the distribution? So we're looking at NP times 1 minus P. So that's 120 times 0.15, again, times 0.85. We've already done this calculation, but I'm just reiterating it, which we saw was 15.3, which is definitely greater than 10. So once we have that, we know that p hat is normally distributed, and we know what the values are here. All right, once we know the distribution, we can now compute a probability. The probability we're interested in is how likely is it to get a proportion, oh, not 26, a sample proportion that's greater than or equal to 0.217. So we're going to see how basically what we're looking at is okay, let me say it this way, because this might be confusing to some. Why am I computing this particular probability greater than or equal to? Last time we looked at less than or equal to. So the reason is that if you think about the picture of the distribution, it has the mean at 0.15. Now 0.217 falls to the right of that mean, whereas before 0.12 fell to the left. Now, since this falls to the right, I'm going to be interested in the area to the right of that number. Whereas in the other case, it fell to the left, so we're interested in the area to the left. So since I'm interested into the area to the right of this particular value, I'm going to use a greater than or equal to. The idea is, let's look at how much area we have here. If this is a large amount of area, then we know that this number falls within the hump. If it's a small amount of area, then we know that we're just somewhere in the tail. Okay. So this, again, we can use the normal CDF to compute this for us. Normal CDF, lower bound of 0.217, right? Upper bound of infinity. So I'm just use E10. A global mean of 0.15. And the standard deviation, which I ought to just put down a number, which is the result here. It's the same thing that we used last time. I'm not going to keep writing it. So without the square, just the square root. Let's see what we get. Sorry for the sniffles, by the way. It's kind of annoying. Got allergies. All right. So let's do it. Second, FARS, normal CDF, put in all the numbers, lower bound, 0.217, upper bound, something very large, 10,000, 1 million, something like that. A mean of 0.15 and a standard deviation, and I'm just gonna put it back in here again, because I don't feel like writing down the number. The advantage to doing the computation inside of the function like I do is I don't have to round, and so I get a more correct, a more precise result. Pardon me, y'all. Well, that was sufficiently gross for all of you, but life is the way it is. Enter. All right, so we do this computation and we find that the probability of having a value greater than or equal to 0.217 is 0.199. Okay. So the question is this unusual? Well, as we learned, if the probability is less than 0.05, then we claim that it's unusual. All right, so this is less than 5%. This is 2%. So this is an unusual sample to have taken. That's what we're saying. We took a random sample from the population. We got a sample proportion of 0.217, which seemed kind of large. But in order for us to actually determine whether that's a large number or not, we need to compare it to the standard deviation, which we essentially do by computing this probability. So this probability takes, is dependent upon the spread of the bell curve, right? So it depends upon the standard deviation. We have to put that in. So we compare this result 0.217 to the spread of the distribution, and we find that this 0.217 actually is way down in the tail somewhere. So when we find the area to the right of 0.217, we get a very small number, and we see that only less than 2% of all samples will have a sample proportion greater than or equal to 0.217. All right, so that should set y'all up.
Daddy?